All right, thanks for checking out this recording. Let me make sure it's working. Yes. What I want to do is I want to finish the reactions for the Qualitative Analysis lab. So in the report sheet, you're going to turn in all the reactions. We left off talking about the red lake and the pale yellow or yellow barium chromate precipitate. So the red lake indicates the aluminum ion was present in our original unknown, and the barium chromate, we would have barium ions present. And so we wrote down the reactions for that. Here is the red lake. This is the red precipitate here. Write down precipitate. Let's see. And here's the yellow barium chromate, yellow precipitate here. All right, so what we're going to do is we're going to look at the remaining reactions that we have. The remaining reactions are off this branch here. So we have the remaining cations. The remaining cations are going to be, let's see. Oh, we weren't testing for barium, we were testing for chromium. And so this barium chromate precipitate means a positive test for chromium ion. And this is chromium 3 ion in our original unknown. So now we're looking at calcium, magnesium, nickel, zinc, and sodium being left. Okay, so to those remaining, we're going to add ammonium oxalate, and the only one that's going to precipitate is calcium oxalate here. So let's continue the reactions here, and I'll write it down here. Let's see. So the remaining ones, we're going to have calcium and I'll just look on the other sheet here. Magnesium, nickel, zinc, and sodium. Let's see if I can remember those. All right, so if I have a solution like this, then I'm going to add some oxalate ion to this. And the only one that should precipitate will be the calcium. And so the net ionic equation will just be calcium plus oxalate. This is going to yield calcium oxalate. Here, that's a solid precipitate. Now, if we have magnesium, it turns out it doesn't form a precipitate. So plus oxalate yields Nr. And then nickel doesn't precipitate with oxalate either. Yields Nr. And zinc does not precipitate with oxalate. This yields Nr. And sodium does not precipitate with oxalate, which would yield Nr here. And so we end up with a precipitate of calcium oxalate solid over here. Okay, then what are we going to do next? Okay, so what we're going to do is we're going to dissolve the calcium oxalate in hydrochloric acid. Okay. So the next step is to dissolve it in hydrochloric acid. That yields the calcium ion here. And so what we're going to do here is we'll do the KSP equation. Calcium oxalate solid. It's going to form calcium ion plus oxalate. Now oxalate's a base, and so the acid will attack the base oxalate. And this is going to form hydrogen oxalate ion here. So what we can do is we can combine these two, as we're looking at KSP. And this is, maybe we should do hydronium here. Then we can see it a little bit easier. Because if I make that hydronium, it's going to be hydrogen oxalate plus water yields hydronium plus oxalate. And so this is 1 over Ka for hydrogen oxalate, which is, well, the scenario we're going to have is Ksp small, and then this reaction should have a large Ksp. And so the net reaction here to dissolve this is we're removing the oxalate, which is going to shift this equilibrium to the right. And so different ways we can think of it. Another way we can think of this is the combined equation here. In the combined equation, the oxalate cancels out. And therefore, if we increase the acid, it's going to shift this to the right, the net equilibrium. Okay, so once we dissolve the calcium oxalate, then the next step in this procedure is we're going to do the flame test. And calcium should yield a red brick color to the flame, or impart a red brick color. And so let's go ahead and write that here. Put this solution in the flame, and then we get a red flame. The red flame doesn't last very long. It burns out quite rapidly. And so in the flame, what are we doing here? Okay, so for the reaction in the flame, usually we have calcium 2 ions in the aqueous phase. Then we put this into the flame, so we get calcium 2 plus ions in the gaseous phase. And then there are free electrons in the flame, and the free electrons can reduce calcium ion to calcium, the element, in the gaseous phase. And then the flame imparts energy to this and excites it. So the calcium becomes excited. This is excited state. Energetically excited. Yes. And then what happens is eventually that's going to drop back down to its ground state. And so we'll have calcium atoms plus H nu, red photon here. Since energy is conserved, the excited state is going to lose energy, to go back down to the ground state and emit a red photon in the process. And so that's the flame test. Okay, let's move on to the other ions here. So we separate out the calcium, and then we're left with the remaining ions here. And then we're going to evaporate to remove the ammonium, which is an acid, yes, and we'll add sodium hydroxide to this. The sodium hydroxide will also, the sodium hydroxide, if there's a lot of ammonium in there, then that could potentially cause it to react with the ammonium. And so you have to add a lot more sodium hydroxide. So if we take the ammonium and then heat it, probably what we'll do is we're going to dry that off, probably as ammonia. Okay, and so we could have different reactions take place here. Let's take a look at what the lab analysis says. So we could have that react in different ways. All right. I looked at the book, and they are looking at two potential anions with this. And so the potential anion would be something like chloride here. So if we have chloride present, then what's formed here is ammonia plus HCl. This would be aqueous. This would be aqueous. And these two would be gaseous. There. So to dry that off. However, the other potential anion could be nitrate. And if nitrate's in there, we're going to form different products, nitrous oxide plus water, gas in this case. Now, the top one is just an acid-base reaction. The bottom one is the redox, because the oxidation states change. Here, ammonium has an oxidation state on nitrogen of -3, and nitrate has an oxidation state on nitrogen of +5. So this is the removal of ammonium. Okay, heat to remove ammonium. Oops, this was supposed to be with plus the chloride here. There. All right, so now we could add our sodium hydroxide, and we don't waste a lot of sodium hydroxide neutralizing ammonium, which is an acid. So the sodium hydroxide, will it react with magnesium? Yes. It will react with magnesium for magnesium hydroxide. Will it react with nickel? Yes, it should react with nickel from nickel 2 hydroxide. Will it react with zinc? Yes, it should react with zinc from zinc 2 hydroxide. Or zinc, not zinc 2, zinc hydroxide. There's only one charge. Zinc. Will it react with sodium? No, it's not going to react with sodium. And so what are the reactions for this? The reactions for this is if we have magnesium ions, then we're going to get 2 hydroxides from the sodium hydroxide, and we can form magnesium hydroxide here. And then if we take nickel 2 plus 2 hydroxides, that's going to form nickel 2 hydroxide, which is a green precipitate. This is a white or colorless. This is a green. And then zinc 2 plus 2 hydroxides. This is going to yield zinc hydroxide. This is a white or potentially colorless precipitate there. So these are all solid PPTs here. Whereas sodium ion is not going to do anything. Is that the remaining here? Go back up. Okay. All right, so we get those 3 precipitates. However, when you look at this, it turns out that zinc forms a tetrahydroxido complex. And so what we're going to do is we're going to add excess zinc. And we add excess, not zinc, excess hydroxide, sorry. So when we add excess hydroxide, this is what happens. Did I do the sodium? There's no reaction? No, I haven't. So over here, I'll do sodium plus hydroxide yields NR, no reaction. And that completes it. And so we have our excess hydroxide here. So let's go ahead and test each of these with excess hydroxide. So I'm going to bring it over here like this. And so magnesium hydroxide, solid, plus excess hydroxide yields NR. No reaction here. Nickel hydroxide, solid, plus excess hydroxide yields NR. We can look this up. We aren't going to form hydroxide complexes this. However, with zinc hydroxide, if you add too much hydroxide, the zinc precipitate disappears. And so if we add 2 extra hydroxides, in this case, we'll form ZnOH4, 2 minus. And so we get a reaction here. The precipitate disappears. Only the zinc precipitate. The magnesium and nickel stay put. And so let's branch off here. And so we're going to get magnesium and nickel 2 hydroxide. Okay. The next step of this is we're going to, and this is strange wording, this green precipitate, they want you to add ammonia until you get a negative test result for nickel. So what they mean by that is, what we're going to do is we're going to add ammonia. A hydroxide complex doesn't form, but an amine complex does form. And so that's going to remove the ammonia here and leave just the magnesium. So they set it until you get a negative test result for this. So let me complete this up here. This is with, I did already complete that. This is with the excess hydroxide here. All right, so we took advantage of the hydroxide complex of zinc forming. We can also look at the complexes in Appendix D and then see that nickel likes to form an amine complex. And so if we do this, what we're going to do is we're going to add excess ammonia. When we add excess ammonia, nothing happens to the magnesium hydroxide, it just stays. So we'll have the magnesium hydroxide over here. However, with the nickel, what we're going to form is we're going to form the amine complex of nickel. And so we can take a look at Appendix D to see, what it likes, or we could we can see other things as well. So the reactions that are happening here is, maybe I should do a different color for the reactions. Magnesium hydroxide, solid, plus excess ammonia. We don't form a nice stable amine complex, so we'll just say NR. However, with the nickel, we do. And so the nickel 2 hydroxide, what we're going to do is we're going to do the KSP equation. Magnesium also has a KSP equation here. But when we do the KSP, this is going to form nickel 2 ion plus 2 hydroxide. Now, with the nickel 2 ion, we can just add ammonia, excess ammonia. And so nickel 2 plus excess ammonia. In this case, we're going to form the hexamine, as I recall, complex. And so we could look it up in the book as well. But we're going to form the hexamine complex here, which is pale violet color. And to form the hexamine complex, we'll need 6 ammonias. Okay, and this is going to give us the hexamine nickel 2 ion. Here. And so they said add excess ammonia until you get a negative result for nickel. A positive result is this green precipitate that we formed in the previous step. A negative result is to get that green precipitate to disappear. So when you see the green precipitate completely disappear, that's a negative test result for nickel. All right, now what we have over here is we have our magnesium hydroxide solid. And let's see, we're supposed to do that. Oh, what we're supposed to do with that is we're supposed to dissolve it in acid and then use the magnesium reagent and reprecipitate it. And so we'll write down those equations. Just a moment here. Pause it. Okay, so it's probably best to break these up into two steps. So the first step would be the HCl. So in this particular reaction, we could do it two ways. We could do it, KSP. This would be like chapter 19 style. So chapter 19 style would be, we have the magnesium hydroxide here, solid. And this is going to go to magnesium ions, plus two hydroxides, like this. And then we're going to add acid to this, the H plus or the HCl. Doesn't matter. We'll do HCl. This, and then we have two hydroxides here, so we'll do two HCl's plus two hydroxides, and this will yield two waters plus two chlorides. And then we can combine these two. Combining these two, we'll have magnesium hydroxide solid plus two HCl's. Now the two hydroxides cancel out, and this is going to yield magnesium 2 plus two chlorides plus two waters. So this is like chapter 19 style way of doing it, or we could do a metathesis. If we take the metathesis route, it's just magnesium hydroxide solid plus two HCl's. And this is going to yield magnesium chloride plus two waters. Driving force is going from stronger acid to weaker acid, stronger acid to weaker acid. Here, HCl being the stronger, water being the weaker. And so, or double replacement, I should say. All right, once we get the magnesium hydroxide to dissolve, we're going to just reprecipitate it out. And so we end up with magnesium 2 plus here. And then, but in this case, we're going to precipitate it out with the magnesium reagent present. And so here, with precipitating out with sodium hydroxide. So magnesium reagent plus sodium hydroxide, sorry, less and less legible. And so I'm just going to write this as a net ionic, so plus two hydroxides. Now the magnesium reagent acts as a dye, and so we just need a little bit in there, not some fixed stoichiometric amount. And so what that's going to do is it's going to precipitate out magnesium hydroxide, but normally magnesium hydroxide is white to colorless. And so this is going to be colored here, and this is solid here. And the color is very distinctive. And so here it says we formed the blue lake. Now it's a kind of a low density precipitate. And so if you centrifuge it, the blue lake settles on the bottom, and it's just like a layer of gelatin. So it looks kind of like a lake, but it's a solid precipitate, magnesium hydroxide. Now, that's the last equation. So if we get the blue lake, that's a positive for the magnesium ion being present. Okay, now we're able to dissolve all the nickel, hopefully. Hopefully there's no residual green in there to form the hexamine, which is kind of a violet color. complex. And so here we have the hexamine. This is 2 plus. It's not 2 minus. We'll call it hexamine nickel 2 ion. And then we're going to just precipitate it out with DMG, dimethyl glycoxamine. Glycoxamine. I don't know pronunciation on that. My pronunciation not so great. And this will be the DMG. Since sometimes we use abbreviations for this, so I'm going to use an abbreviation for the formula. I wouldn't use an abbreviation for the name, however. And so normally these complexes are quite stable. However, turns out this DMG precipitate is going to be more. So, let's see if we get back there. There are two ways we could do the more of a Chem 1B style. That is magnesium hydroxide, solid, or actually, no, I don't want to start there. Let me fix this. The hexamine, 2 plus, here. So the chapter 19 way of doing this would be something like this. For these, we look at the other direction rather than here. Actually, maybe I'll leave it. But anyway, we would take a magnesium 2 plus 6 ammonias. That's going to give us the MgNH3. Six 2 plus species. And then we're going to attack this with DMG. So what's going to happen with the DMG is it's going to attack the magnesium here. So we'll take 2 DMGs and magnesium 2 plus. We're going to form DMG2 solid. And that's what we have here. It's a red precipitate. Okay. Now, red precipitate would be a positive test for magnesium. Okay, let's go back and take a look at the remaining species here. The remaining one would be zinc. And so we did the excess hydroxide. We got the zinc to dissolve. And we formed the tetrahydroxide of zincate 2 ion. And then we add the potassium hexacyanoferrate 2 and the hydrochloric acid. And then we form this, the ZN3 from K2. How many complexes do we need? 2 complexes. So that's on this branch over here. So I'm going to branch off here, and then we're going to have this ZnOH4 2 minus here. Then I'm going to drop this all the way down. Here. Okay. So basically, it looks like they're just adding this potassium hexacyanoferrate and HCl. Okay, the purpose of the HCl is to break up the complex to free up the Z and 2+ ions. And so let's do that reaction first. One is we're adding HCl. And so if we have this, the KF reaction, since we're dealing with chapter 19, I'm going to do it this way. Let's check. So we have Zn2 plus and 4 hydroxides, which is going to yield ZnOH4 2 minus. All right, the HCl is going to remove the hydroxide here. So there are different ways we could do it. We'll just do 4 HCl's. This is going to form 4 H2O's plus 4 chlorides. Okay, so and there are different ways we could set this up, but this is one of them. And so this is going to shift to the left and eventually destroy all the complex, replacing with Zn2+. Now the Zn2+ can react here. So the Zn2+ can react with the form Zn3 and then 2 of these cyanoferrates. So that's step 1. And let me just do it a different way here. Or alternatively, we could take the zinc, the tetrahydroxide of zinc K complex, and then add HCl. And this should give me 4 waters plus any unreacted hydroxide complex. But assuming that we have it completely reacted, then we just end up with Zn2+. So two different ways. You can do the Le Chatelet shift here, or you can do it this way here, the Zn2+. Okay. So once we do that, then we're going to add the potassium hexacyanoferrate. Like that. And then what we're going to have is we're going to have a precipitate. It's going to have 2 of these. Two of those is going to make it -8. And so we need +8. And to get that +8, we're going to take 2 zincs. Actually, those are +2. And we need -4. And so, what do we have here? We end up, to get the correct ratios, 3 zincs, it gives us a -6, and then 2 potassiums, which gives us +2. That gives us -6. And then we have the complex here. Actually, let me correct that in just a moment here. Pause this. Okay, and so we need 3 of the zincs and then 2 of the potassiums. And that should add up. And this is an unusual precipitate here. And so the zinc is 2+, zinc is 2+, zinc is 2+, and then potassium's plus, potassium's plus. So this is minus 2, 4, 6, 8, minus 8. And then we have 2 of these. And so this is plus 8, sorry. We have 2 of these, this is going to be minus 8. Okay. And these add up to plus 8 here. And so electrical neutrality is maintained. So we get a nice blue precipitate from this. And that would be a positive test for zinc. So blue precipitate. All right, let's take a look at the remaining cations here. It would be ammonium and sodium. So let's take a look at those two. Those will be the last two I'm going to talk about in this video. So the ammonium test is we take some ammonium here and then we add some hydroxide. And what that forms is ammonia plus water. The problem is ammonia is very soluble, quite polar. Okay, but the ammonia here that's formed is going to be in the aqueous state, and so it's hard to detect sometimes. But what we're going to do is, since we're adding strong base here, it could have contaminated the solution. So pH isn't going to tell us alone. What we're going to do here is we're going to heat it, and so what we're trying to accomplish with the heating is to drive the ammonia out of solution into the gas phase, and then test the gas for acid-base properties. So, for example, if we know that the top of the watch glass here slowly turns blue, then that's due to the presence of ammonia gas. So, slowly or gradually turns blue. And so the way we can say is the gas is going to come in contact with the wet litmus, so called just H lit here. And if I do that, then I'm going to form ammonium ion and then the whatever the color anion is. Okay, so what's important for this is that the ammonia gas gradually turns the red litmus to blue. The red litmus is an acid. So we have an acid-base reaction here. Okay, and this is a piece of litmus paper stuck on the bottom of the watch glass. And so this would be a positive test for ammonium. For the sodium ion test, it's just this. We have our sodium ion aqueous, and then we put it into the flame, so that makes sodium ion gaseous. This is flame. And then in the flame, there are free electrons floating around. So in the flame, the sodium ions can get reduced to sodium elemental sodium atoms, metal, in the gaseous phase. And then in that flame, the sodium atoms get excited to some excited state in the gaseous, but they don't stay there forever. Eventually, they're going to drop back down to a ground state. That is, electrons will drop back down to ground state. Sodium gas is not the ground state of that element, but the electronic configuration, plus a photon. This one is a bright yellow or bright orange, yellow-orange flame. Now, the situation with this is this one gives a lot of false positives. This test, this test gives false positives because your fingerprints contain sodium, and it gives you very positive, bright test results. So this test gives false positives because of sodium contaminations. Okay, that's pretty much the remaining reactions there. Thanks for checking out this video. I'll post another one tomorrow night, probably.